Hello there, welcome back, and this is part two of our spherical tank problem. Um, and in this part, we're going to be coding to find our initial inlet flow rates that we derived in part one, and then we're also going to be coding to find our changes in heights if we were to change those and change the inlet flow rates so it's no longer at a steady state. We'll see how the height changes. And we're going to graph the change in height and our change in our inlet flows. So to begin, I'm going to go ahead and just import a couple plugins that will help me calculate these and plot the graphs. So from So that is our solve IVP, or solve our initial value problem, which will help us. That's basically going to be what calculates our changes in heights. And then I'm also going to want to import JAX, which is Google's machine learning program they wrote. And from that, I want to import jax.numpy. I'll abbreviate that as JNP. And that's going to help me do some of these calculations. It'll just give me access to like square roots, absolute values, things like that. And then for the plots, I want to import Plotly. This will just let me plot them. And from that, Plotly.plots. There. So that's everything I want to import. Basically just helping me either make the plot or calculate my functions. So the first thing I'm gonna want to do, let's go and just review what the problem is. So we have two spherical tanks that are open to the atmosphere, and they each have a given radius. And they're connected. Tanks 1 and 2 are connected by a pipe that has an area of 0.2 meters squared, and the second tank also has like a whole pipe that's of the same area that is draining tank 2, and both of them have the inlet flows going into each of them, and they're at an initial steady state with given heights. So the first thing I want to do is I just want to plug in all my knowns. So everything from that we are given. So we know the R1 is equal to 4, R2 is equal to 2. The areas of the two tubes connecting them and leaving tank 2 was equal, and they were equal to 0.2 meters squared. I know my initial heights. H1 is 5 and H2 is 3. And then I'm also going to just calculate the square root of 2g now, so that way I don't have to keep calculating it. And that's just going to be 2 times 9.8, square root of that. There, so those are my knowns that were given. Now let's use what we knew from part 1, where we derived our equations. So we know that the flow between 1 and 2, initially, we found that, and it was equal to the area of that pipe times the sine of H1I minus H2I. That's going to be multiplied by the square root of 2g, and that's going to be multiplied by the absolute value of H1 minus H2I. There, so that's the flow between the two tanks, and then we also knew the flow, the initial flow leaving tank 2, and that was the area of the pipe times square root of 2g times the square root of H2I. And then we were also able to derive and find our initial inlet flows. So Q1Ni we knew was equal to the flow leaving tank 1, so Q12I. And for the inlet flow for tank 2, we knew was equal to the flow leaving tank 2 minus the flow coming in from tank 1. There. So that's all of our knowns. That's all of our knowns. So let's see what the initial inlet flow rates were. So we can just print an F string, and we want Q1Ni equals Q1Ni Q2Ni equals Q2Ni. There, so those are the initial inlet flow rates that are keeping our tank at steady state. But let's say we were to change those. How is our height affected? So we want to start with defining functions for our inlet flow rates given time. So function given a time, and we want to return. Let's say that the inlet flow to tank 1 decreases by 10% over a certain time. So we do Q1n initial minus T over Tn. So Tn is going to be my final time, and I'm just going to say that's going to be equal to 500 seconds. And then that's going to be multiplied by 10% of Q1n. And then, so that's going to decrease our our inlet flow rate for tank 1 by 10% over 500 seconds. And for tank 2, let's increase it by 20% over the same time period. So we want to return Q2Ni plus T over Tn times 0.2 times Q2N. Forgot. There. So that will give us, increase our flow rate into our second tank by 20% over that time period, and decrease the one into the first tank by 10% over that time period. Syntax error. There. Okay, so now we also derived from part 1 how we could find our change in height over our change in time, and it was equal to, for tank 1, it was equal to the flow coming in from the inlet minus the flow leaving, and then that's going to be over our cross-sectional area that we also derived in terms of height in part 1. And those are equal to, I'll just set them up here. So a cross-sectional area of tank 1 is equal to pi times the radius of tank 1 squared minus the height at 1 minus the radius of tank 1. And then that is going to be squared. Right? Yeah. So, and then for the area, cross-sectional area of tank 2 will be equal to the same thing, but with the radius of tank 2 and the height of tank 2. So R2 squared minus H2 minus R2 squared. Shift enter. Why? What? Oh. I don't know where that came from. H1 is not defined. Oh. Okay, never mind. I'll just plug them in down there. I forgot it was gonna be annoying like that. Okay. So let's make a function that will find dH/dt. In our plugins we want time as our first one, and then we want our heights for tanks 1 and 2. So that's going to be an array. Okay. So I want my height at tank 1 to be equal to the index, the first index of my array, and the height of tank 2 to be equal to the second index of the array. Okay, and now we need to find our change in our flow rates between tanks 1 and 2 and leaving tank 2 given these changes in heights. So we can just copy and paste this equation down. And let's go ahead and just create it. So it's not initial, so it's not the initial heights or initial flow rates, it's what we get from the change in time. So we just get rid of all the initial values. Okay. And then I'm going to want to return an array that will hold the values of the changes in height in tank 1 and tank 2. So I just need to do Q1n minus Q12. And then this is going to be divided by the cross-sectional area that I was trying to define, but so the pi times R1 squared minus H1 minus R1, and then that is going to be squared. So that will be for tank 1, and for tank 2 we have Q2n plus Q12 minus Q2 might have way too many parentheses, and then divide that by the cross-sectional area, so it'd be pi times R. Oh, what happened? Whoops. Pi times R. R2 squared minus H2 minus R2, and then square that. Shift enter. There. So that gives us, so that will put into an array our changes in heights over time. So let's go ahead and solve our initial value problem so we can get that. So we'll go solve IVP. And so the first thing we want to do is put in the right side of our equation, so dH/dt, that function. The second thing it's calling for is our our span over what we're integrating. So from 0 seconds to t end, which was going to be 500 seconds. And then the next thing it's calling for are the initial values that we give it, so h1 and h2i. And the method we're going to use is rando. I think that's how you say it, R-A-D-A-U. And I want the dense output to be true. There. What did I do? Unsupported operator times 4. Q1N. Do I even need these parentheses? What is wrong? Let me look at my code I already wrote for this. What did I? Oh, okay. I see what I did wrong. I forgot my t's there. Forgot to make those as a function. Oh man. There we go. Okay, so now this is giving me so these are the times. This is going to be my heights, change in heights for tank 1, and this will be the changes in heights for tank 2. So the next thing I'm gonna want to do is I want to make basically a variable that's going to be so tplot is going to give me points for every second between 0 and tn. So 0 to 500, it's going to give me points for every single second. So to do that, we just go jmp.linspace, and we want our start. We want 0 to t-end, and I want a point for every second. So I have 501 points, 501 seconds, 501 points. And then I'm gonna clean up this data a little so we can graph our plots. So to do that, we're gonna use this solution, the sol function that they gave us. So we do, I have to name this, I'll just name it res for results. And then sol is going to equal res dot sol, and I want the heights for each second. So for tplot, shift enter, sol, there. So that will give me, those are the heights for every single second, and there's 501 of them. So now we can just go ahead and let's graph this. So fig is going to equal make subplots, rows. I just want one row and one column for now. One row and one column, and then I want to add my graphs into these subplots. So fig.add trace, graph objects, and I want a scatter plot, and I want my x to be equal to tplot. So my x is my seconds, 1 second for every point. And my y is going to equal the first index of that sol, so sol 0, and we'll name it height 1 because that's the index that I'm getting, and the same thing for height 2. X equals tplot, and my y is going to equal the second index of sol, so 1, and that is going to be height 2. Shift enter. Argument follows keyword. Huh? There. Those are my change in heights with this given, with our change in our inlet flow rates. And we can also go ahead and graph our change in our inlet flow rates. So let's just copy this down. Let's make you Q1N, Q2N, and for the y I want it to be Q1N, our function, and I want tplot as my t. Same thing for this, Q2N, tplot. Shift enter. There. So it's kind of hard to tell if anything's really even happening, especially for these flow rates. But we can, let's put these in onto different graphs. So let's make 2 columns and we'll put you in row 1, column 1. Row 1, column 1, row 1, column 2, row 1. There. Okay. So now I have my two plots. I have my flow rates on this one, and I have my heights on this one. There. So that solves for finding our change in heights with the change in flow rates, and we graphed it all. But let's make it a little bit more complex. Let's say instead of the flow rates decreasing by 10% or increasing by 20% over a given time, let's say they stay constant and then someone flips a switch and the inlet flow for tank 1 increases by or decreases by 20%, something like that. And the same thing, someone flips another switch at, like, let's say 200 seconds, and the inlet flow for tank 2 is increased by 250%. How could we do that? So we want to come back up here and look at our functions we wrote here. And what we want to look at for the switch, how could we graph this switch? Well, if we look at this function called a sigmoid function, you can see that it takes any values and it squishes them between -1 or 0 and 1. It squishes them between 0 and 1, and it goes off to negative infinity and positive infinity. So we can use this function and then just we can manipulate it and transform it. We can add something to make it go higher than 1. We can squeeze it so it's a sharper increase, and we can we can do a horizontal shift, a vertical shift, so we can get it where we want it. So to do this, I'm gonna just get rid of this code right here. I want to define a function. I want to define my switch function. And with this, the things I'm gonna want is I want the time that it's happening. I want my initial position. I want my new position. I want the time it's going to switch at. And I want some sort of scale that it's going to be. So that will give that. So I'm making a function here. So V1 will be equal to, if I put it in terms of the inlet flow for tank 1, V1 will be the initial steady state flow. And V2 will be the new flow after I change it by a certain amount. And T switch will be the time at which it switches, so 100 seconds. So what we want to return here is sigmoid there. And so if I do T I do T minus T switch. This will give me a horizontal shift to where I want it to switch at. So if I put in 100 for T switch, it will move it down to the 100-second mark. And if I divide that by the scale, that is going to cause the compressions or the or pulling it. And then the next thing I want to do to transform this is if I multiply it by I want to multiply it by my differences in my values. So V2 minus V1. And then I want to add my original value on there for my vertical shift. And this should give me my the transformation that I want. So now that we have that, we can come back down to Q1n, and we want to return our switch function, and T is just going to be time. Our initial flow rate, so Q1ni. Our new flow rate, so we want it to decrease. We want it to be 80% of its original flow rate after 100 seconds. So 0.8 times Q1ni. And we want this to happen at 100 seconds, and we're just going to keep the scale at 1. Did I hit? Shift enter. And now for Q2, we want to do the same thing. We want to return the switch function for time, and our initial is going to be Q2ni, and we want this one to increase by 250%. So we do 2.5 times our initial flow rate, Q2ni, and we want this to happen at 200 seconds. And again, the scale will be 1. Shift enter, and wait for this to go. So here are our new changes in heights. Let's see how they look on the graph. There. So obviously the changes in heights are much more complex than what they were. You can see these dips, these gains, and you can see how our switch function, it looks like how we manipulated the sigmoid function. We stretched it, it goes between these 2 points, and we have a little switch right here where it switched from the top point down to the bottom point. And we used our knowledge of manipulating functions with transformations to do that. So you can see how the inlet flow for 1 decreases by 80% here at 100 seconds, and the inlet flow for 2 is going to increase by 250% here at 200 seconds. And that answers our questions that we are wondering. So we have these 2 spherical tanks with these dimensions. At t equals 100 seconds, the flow of the first tank is reduced to 80% of its initial steady state, and then at t equals 200 seconds, the flow of the second tank is increased by 250% of its initial steady state. And we showed how you can graph the changes in heights and find that for that. Yeah, that was a fun little project right there. Hope you guys enjoyed.